We're now coming to part 3 of gravitational fields, and we're going to look at satellites. So here we have a diagram of a satellite in orbit around the Earth, and we know that the gravitational force on the satellite, which is represented by the letter F, is equal to G, the gravitational constant, multiplied by m1, which is the mass of the satellite, multiplied by m2, which is the mass of the Earth, all divided by r squared, where r is the radius of the orbit. Now we also know that from Newton's laws of motion, if a force acts on an object, it must accelerate. Well, you might say to me, well, the velocity is constant. The magnitude actually of the velocity may be constant, but as you can see from the diagram, its direction will always be changing, so velocity isn't actually constant, and it's not constant because there is an acceleration acting upon the satellite. We also know from Newton's laws of motion that force equals mass times acceleration, so the gravitational force must be equal to the mass of the satellite multiplied by the acceleration due to gravity. And finally, we can see that the acceleration caused must be in the same direction that the gravitational force is acting. So you can see that quite clearly shown on the diagram. Now, if we want to expand this a little further, we know that an object in circular motion must be in circular motion due to a centripetal force. And what's the centripetal force being caused by? Well, it's been caused by the gravity, so the gravitational force must be equal to the centripetal force. And if we take the equations for both the gravitational force and the centripetal force, there we are, we have those equations expressed there, and one must be equal to the other. So if we rearrange those formulae there, we find out that v, the velocity of the orbiting satellite, must be equal to the square root of g, the gravitational constant, multiplied by the mass of the Earth, m2, divided by the radius of the orbit, r. Now let's take this a little bit further. Let's think about how long the satellite will take to orbit the Earth. Its velocity v must also be equal to the distance it travels divided by the time it takes. So the distance travelled around the circle is just the perimeter of the circle, which is 2 pi r. R is the radius of the orbit. And the time is the time taken for one complete orbit around the Earth. That's denoted by the letter t. And if we rearrange that equation, we can find that t, the time taken for the satellite to complete one orbit, must be equal to 2 pi r divided by v. Now let's move on to an examiner's favourite question. This looks rather horrible, but quite often they will ask you to prove that t squared is equal to 4 pi squared r cubed divided by g m2. So how do we do this? Well, first of all, we take the equation for t. T equals 2 pi r over v, and we square that. So we get t squared is equal to 4 pi squared r squared divided by v squared. Second step. We learnt from the previous slide that the velocity v is equal to the square root of g m2 divided by r. So if we square that, we get that v squared equals gm2 divided by r. And then all we need to do is substitute that formula into the formula that you derived for t squared below. And when you do that, you come out with the conclusion that t squared is equal to 4 pi squared r cubed divided by gm2. And that's the end of part 3.
Created using Powtoon.